I work at a engagement entity at the university called ENSA, and ENSA was established in 2002. So we've been in business for 22 years. What we do mostly is support of industrial services, so typically in the automotive industry, and most recently in power generation and petrochemical. So we do a lot of work for Eskom and for Sasol, and because we have the experience with for Eskom and Sasol, we typically have typically have experience in automation, machine design, product development, and this is what we've now decided to bring to to marine robotics. So ENSA, our innovation through engineering, has been our slogan for many years, and we've been offered money for that. So there's value in almost anything that you can come up with. Those of you that don't know our coastline very well, we're in Port Elizabeth, so we've got the sea right at our doorstep, and this is water harbour in Africa, as far as I'm aware, but certainly Southern Africa. So that makes Nelson Mandela Bay a really attractive place to have a business. And like I said, when you speak to an audience, make sure that you tell them everything 3 times. So I'm going to speak a little bit about ENSA. I'm going to talk about the problem that we need to solve, and then I will give you a little bit of background about what we plan on doing about it. So ENSA is, like we mentioned, an engagement entity, and you need to ask what exactly is an engagement entity. And basically that's a unit at the university, completely self-funded, that's been doing work in engineering, testing, R&D, product development. And we now have a group of 72 staff. We have, I think we have a number of about 40 engineers in our group, and that makes it very special globally. A lot of people don't really know, that the University of Port Elizabeth or Nelson Mandela University is sitting with this little nugget of innovation that can do work and solve problems for South Africa. So we've been divided into a number of specialized areas within our group, and this is something that we manage. So we decide what these groups need to be, and we have a government program that we work. So this is a national program called UELAW, and that looks at e-mobility and bringing the electric vehicle to South Africa. And a lot of us in South Africa will wonder how on earth Eskom is going to be powering those cars. The truth is that Eskom will never power them, but everybody installing solar will now be able to charge their car as well. And as soon as we stop thinking about a car as a mode of transport, but rather as a mobile battery, it changes the entire perspective. So a little thing, when you get home in the evening, you won't be plugging your car into charge, you'll be plugging your house in. So all those immediate demands that you would generally pull off the grid, causing that initial peak, would now come out of the car. So as soon as a lot of people, as they go into park their car outside the house, they would open the garage door, they would wash their hands, and that subsequently turning the geyser on. They would check what's in the fridge, so the fridge would come on, the lights would go on, the geysers come on, and then they would check to see what's on TV before cracking open the first beer. And that would be, every hard-drawing piece of equipment in the house has come on all at the same time. So that energy can come out of the car. So it makes it a really valuable tool to actually have, but that infrastructure needs to be created. That's what that program is really all about. Then we have a training academy. Is used as a vehicle. So we have, as being at the university, we have access to staff, John being one of those, that is able to offer specialized training to whoever needs it. And we can effectively offer training to staff starting at 8 in the morning, and then have that training stop at 10. That staff member at the factory can then get his day started and work through till lunchtime, and then we can do training again until 3, and then he can end his day. So we can reconfigure the training to suit whoever and demand for that. So the whole South African population is made up of people that are completely trainable, and it's something we're experiencing. Our technology station program is a government-funded program that assists us with supplying technology to companies that can't normally afford it. So if, for example, a company wanted to become a supplier to Volkswagen, then they could bring us their components that they've built. We would test them for it, and we would test it against a Volkswagen, or for that matter, a global specification, and give them a certificate for that. Our labs are accredited, and that component could then go to Volkswagen with a certificate of compliance, and that gives you a fair shot at actually getting work from a major OEM. So that's a significant role that we play there. Then on the engineering side, we do some large industrial projects, like I mentioned, for Eskom and for Sasol. And this is primarily on the life extension side of the business. So in the old days, when they built a power station, they would have built it for a 40-year life. And 40 years, we've shown has gone really quickly. And the question is, how much longer can we really operate that power plant safely? So we have developed a technique for removing samples from these high pressure and high temperature components, and we can then analyze the material of that sample that we then remove. What we do at the same time, after removing the sample, we repair that sample site, and that puts our sampling technique on a pedestal, in that we have the only sampling technique that can take a deep sample from a equipment and then repair that site and put that plant back into service, within a couple of hours. So this has received a lot of attention, and most recently from the nuclear authorities in the UK. So a lot of work and development that's gone into that. And funnily enough, if we can extend the life of a power station, that assists the conservation efforts, in that it means there's another power station that doesn't need to be built, which is incredibly damaging. So if we can get the last bit of life out of these pieces of equipment, it's really is a good thing. And then we run a research and innovation section that looks at solid state joining techniques. And the last thing we're looking at is composites. So composites is really the material of the future, and it allows us to build really complex shape really simply. So there's a lot of advantages to it, which I think you will see later. So this is a short clip of those that aren't familiar with our campus. So currently our engineering footprint through South Africa, we do work all over South Africa, obviously Cape Town, Port Elizabeth, Durban, and Johannesburg. And then I think you can see the top little triangle. We've been doing some work in Botswana. We've been doing work in Mozambique. some work in Uganda, and then obviously in Europe as well. So in Europe, primarily in the UK, we've been having a look at the repair on nuclear facilities, and we've been doing some work on marine robotics with the French, and the Germans on machine design. And then in America, they are really interested in our plant life extension program as well. So the whole world has generally got a very similar problem to what we do on aged infrastructure. So yeah, it's a big place out there, and our little center in Port Elizabeth is slowly growing and making an impact. These are typically some of our customers. And that's just about everybody certainly in Port Elizabeth, and globally there's some big players in there as well. This is what our team would look like that goes to Sasol, and each one of those members is an engineer. They were part of the development of our sampling and repair processes, and so when we send our team to site to remove these samples, the team that developed the equipment, that developed the software, that developed the technique, go and actually do the work themselves. So if there's a breakdown on site, they actually repair it themselves. The guys that built the equipment are on the team. So a company like Sasol is highly impressed in that we're completely efficient, which makes a team that's housed at a university very special. Yeah, the images on the right are what a turbine looks like on a power station. So we've developed a grinding technique for repairing those turbines, and then the plant on the bottom right is what Sasol looks like from the air. So Sasol is a giant machine, and they're looking at extending the life of those. And if we can extend their life, those critical components, by a couple of years, it saves a huge big hole that would otherwise need to be dug into the earth to remove more steel. So the reason that we're here tonight is really having a look at how we're going to use those skills that I've shown you in the previous images to addressing some of the we have. So this is a satellite view of Cyclone Freddy. So Cyclone Freddy crossed the Southern Ocean and then continued operating between Madagascar and Mozambique for 5 weeks. So you can imagine that the rain that we've had recently in the Eastern Cape, that was lasted for 3 days, and it was a terrible environment to be in, having that much water come down all at the same time. And the Mozambicans and Madagascans had to suffer for 5 weeks through this rain. The truth be told, the Freddy did cause a bit of damage, but not as severe as it could be. But I think it's important that you have a look at what the land masses look like, just so that you're familiar when we head to the next couple of slides. So this is an image of what the ocean currents look like. And this is typically what you would learn at school, that we have our Benguela current coming up our west coast. We have our Beacon current coming down our east coast, and the Southern Ocean circles in sort of a anti-clockwise direction. The Atlantic Ocean is doing its thing, the Southern Ocean is doing its thing, and that's sort of what we understand as the basic sort of layout, and we try and describe our weather patterns from that. But our sea isn't flat. It's actually three-dimensional. So the sea really is a conveyor belt of systems. So it's not necessarily just as simple as what our top view sort of shows it to be. So it's got these, at depth, we've got some water moving north, higher up it's moving south. You can have warm water from the Indian Ocean move all the way into the Atlantic Ocean. So it's really a complex environment. And if we needed to make a decision based on the temperature of the surface of the sea, we would need to be sure how that warm water on the surface translates to what's actually happening to this conveyor belt of water that's at deeper areas of the ocean. So getting back to that previous image that you saw, so this again is a satellite, an infrared image of satellite, and between Madagascar and Africa, or Mozambique, you have that really hot area, and if you can have a look how hot the water is on the left of Madagascar compared to what's on the right. There's the formation of that sort of bite out of the northern area of Madagascar. It's gotten just that. I think you should be able to discern the additional temperature rise in that of what the satellite image is showing us there. So that bit of warm water is the idea is that bit of warm water is actually feeding the cyclones and actually giving them that little bit of energy to be able to stay in that area for longer. And areas that now needs to be studied so that we can determine and predict whether or not the cyclone's going to be there for longer, or whether they're there at all for that particular reason. So basing this off a satellite image is a little bit controversial, because a satellite image is only measuring that top skin of the water, and with satellites you can get a 2-degree temperature difference between on the same satellite moving over the same area. When it's moving between the day and night. So that's a huge temperature difference, using the same satellite. Had it been 2 separate satellites, I think it would be, you could argue that, it's a calibration problem or something. But just with the same satellite having this 2-degree temperature difference, it certainly is, highlights that there's something happening. And to be able to address that, we need to effectively have a ground truth, to be able to measure what is it actually, what is it on the surface, what is it at depth, to be able to give a real reason, and then use the satellite as a tool for truth, really. So what has been developed is this network. So I think you can see Australia in the middle, and the unusual map below us, but that's the Earth. If you look at South Africa on the very left of your image there, so what we're highlighting here is an Argo float network. So the Argo network is a network of instruments that have been deployed throughout the sea. And I think there are about 4,000 of these instruments in the water at the moment. And they give weather data information all over the place. But if you have a look at Southern Africa, and then particularly that little warm bite out of the top end of Mozambique, we've only got those 2 instruments that are floating there at the moment. So these floats are not propulsion systems or anything else like that. So they're really tricky to move around. If they've been deployed in that area, they'll stay there for a while before they drift onto a beach, or they need to be rescued by a boat or something like that. And Africa is not really a well-serviced area. So if I go to the previous screen, you can have a look at the density around, and particularly look in the Gulf of Mexico. So I hope you can sort of see where that is between South America and North America. And you can look at the amount of instrumentation in the Northern Atlantic. So that's where you typically get your cyclones that would affect the wealthier countries. And then you can see the sparseness that we've got, and the weather that we have in South Africa all comes from the Southern Ocean. You can see how little or poorly instrumented that area is. So this requires a little bit of innovation to be able to address, and this is something that we sort of trying to look at. But to go on to the Argo floats, so the way they work is that they have a buoyancy engine in them, and so it's just a very simple piece of pipe that's got this bladder system inside it. So it's got a battery, a little hydraulic pump, and with that hydraulic pump you inflate a bladder on the inside of this tube, which will make the entire device a little heavier, and then it'll sink down till it gets to a target depth. It'll then stay at that target depth for a specific duration, or however long it's been programmed, and then if need be, it'll go to a greater depth if that's required, and it'll pump a little bit more water into it. It'll stay at the final depth, and for a time period, and then when it needs to transmit data, then it'll pump all the water that's in it out of it, and it'll float up to the surface, and then via satellite transmit that data back to France, actually. And that data is then shared and used globally to be able to assist with global warming measurements, current measurements, and we can use that data in a variety of ways. And if I digress slightly, I think some of you that are familiar with the Algoa Bay area, every couple of months, and particularly in November, December type of area, you'll suddenly get that real cold snap where the sea just absolutely freezes over. And no one wants to be on the beach on those days. The air will be misty. And what's happening is that we get an upwelling of the Rocks area. So that's Cannon Rocks is really flat, and our continental shelf is not really all that far, maybe I think 140 kilometers from the beach in that area. And we get this upwelling, and with that upwelling, a whole lot of nutrients then is pumped up. So we get this cold water, and we get all of this nutrients that is deposited in Algoa Bay, Jeffreys Bay area, and our depends on whether or not we can get this, whether or not this nutrients is actually deposited correctly. So if we don't get this upwelling, then we know that there's going to be a poor charcoal harvest, which means that we're going to have 50,000 people without work, or certainly 50,000 people without food that year. So being able to monitor the ocean currents, being able to monitor the sea conditions and temperatures accurately certainly assists with ensuring that we've got people employed, or that we can predict ahead of time whether or not we're going to have a disaster. So yeah, then the question is, how does Nelson Mandela University play a part in this? So we started an ocean sciences campus in 2017. So we bought the old CSIR campus that was nearby, and we turned that into a completely ocean sciences campus, where they looked at the biology, the oceanography, the law of the sea, various other aspects. And with that, they decided that it'd be really handy if they had this sort of control room where they could have a look at what the sea was doing and get all this information out. And that meant developing this Marine Robotics Center. And the truth is, you don't need this big control room because all the oceanographers would simply get the data sent straight to their desktop. We didn't need the whole big center, but we needed the assets. And we received some funding in 2018 to start developing some of these assets. And those assets included an ocean glider. So an ocean glider is very similar to a Argo float, in that you simply increase its or you decrease its buoyancy by pumping water into it, and then it'll sink. But instead of sinking vertically down, it happens to have wings on it, and those wings will assist it in sinking in a direction. And we can shift the battery pack inside it, which is the heaviest part, and change its pitch angle, and that'll make it go in a direction. So we now have effectively we have thrust, and we have directional control with a very minimal amount of energy input. And this is a really efficient way of getting a single buoy to cover a large area of ocean. So we no longer need this huge Argo network. What we need is, or what we have, are these ocean gliders that can measure at one point and then traverse and across the ocean and then measure in another point. So it is a tool. The sea is obviously a big place, and the more equipment we can have in the water, the better, to be able to give us an accurate indication of what the condition of the sea is. And then in 2020, we received additional funding that assists us with further development of our Marine Robotics Center. And that's taken a sort of leapfrogged us forward. So this is an image of our first ocean glider that we developed, not necessarily all that pretty, and we learned a couple of lessons from it. So what we developed initially was a segmented type of design, where we had the battery pack and the control unit all as in separate sort of segments, like a worm, and that if we needed additional batteries, we would just increase the length of that segment. But the reality is it became very difficult to work inside these little pieces of pipe. So this was our first prototype. We then developed another one. And that's what this one looked like, a very much simpler design. So everything fitted inside a pipe, but we pulled the guts of the machine out on a single skewer. And that allowed us to be able to work on the components really, really easily. So the images on the bottom right, really the circuit boards and pump that's in this unit. It works exactly the same as the Argo float. There's no holes in the vessel, so everything gets controlled with how we shift the mass on the inside, and that's done autonomously. So you program the glider to go to a certain depth, and then rise to a certain altitude. Effectively, is how we would term it, and it then has the sinusoidal motion through the water. Obviously, the deeper the sea, the better. In that its glide ratio is about 1:1, so it's not fantastic. But so if it's in the water depth of 1,000 meters, it can go 1,000 meters forward before it needs to start rising, and then rise for 1,000 meters and take measurements the whole way. And then after about the 10th time of going up and down, it'll then surface and then transmit to the satellites, give us that information, and then go and repeat the cycle. So this is what the CAD model of the unit would look like. I showed you the pictures right at the beginning of the engineers that we had that would work on our welding solutions. One of those engineers was tasked with the job of designing our ocean glider. And the entire team would play a little bit of a part in ensuring that the parts are either manufacturable or the parts are correctly specified for what we're doing. That make sure that the communication protocols are correct, make sure that the antennas are correct and whatever. So we've been able to use the expertise within our entire group to be able to diverge completely from having a heavy engineering sort of impact to something that assists the oceanographers with actually being able to get information from the sea. So I think the primary requirement of the team was ensuring that at least somebody in the team could swim. And I think that's probably where I play a little bit of a part. So this is the assets that we have available to us. So the image in the middle is the glider assembled and prepared for a depth test. And the boat that we're using is owned by SIAB. So SIAB is the South African Institute for Aquatic Biodiversity. They're in Grahamstown. And they've been very generous in making their scientific equipment available to us whenever we've required it. So they're doing some really good work and need support wherever they can get it. And then this is a little video clip as well of a simple test. But I think if you can look in the background, we have a drone that's operating. And you can also see that the drone is geo-stabilized. So it is stable with whatever it needs, with relative to the Earth, and the boat is the thing that's moving. So it gives you an idea of how dangerous this or unpredictable the sea can be on a relatively flat day. So if you can watch that drone in the corner as well, with the corner of your eye. I see it's just a bit out of view now, but yeah, it's not the most pleasant place to be. Those guys that work in the sea deserve every ounce of respect you can give them. It's not an easy environment. Yeah, so again, these are our engineers. They've played a part in designing the equipment and then obviously testing it. So we're very lucky with the group of people that we work with. So being at a university, what we have done is made the opportunity available for students to also experience the sea. And we would take some of our students with on a task like this. So like I mentioned, we are completely self-funded. So our engineers effectively need to earn a salary for all the testing and experimentation they do. This is not for fun, this is their job. And the benefit of having us at the university is that the students would actually benefit from this type of experience. So that's our underwater equipment. We also have built some surface vessels, and I think in the very we showed a little bit on this one. So this was our first sort of stab in the dark of what we interpreted a surface vessel needed to look like. So we built a autonomous boat with so using solar to charge batteries, and then the batteries driving the boat. And this particular unit turned out to be really, really good in that it could survey indefinitely. So when it's in the water, it is equipped with a CTD, and a CTD is a unit for measuring conductivity, temperature, and depth. And the conductivity measure is a measure of salinity, and that'll give you an indication of the health of the sea. So we're getting that ground truth that we spoke about earlier. We're getting the conductivity of the water, which is telling us how much nutrients we should be depositing in our bay, and then getting a depth measurement. So really, really valuable simple survey. And then obviously we've used relatively inexpensive equipment for achieving that. So it's quite an affordable amount of data that we're able to gather relatively easily as well. So this is a clip of a trip that we did to Mozambique, and then need to drop that sound a little bit. So being a trip to Mozambique, we're able to simply take any of these vessels, put them on the top of a bakkie and drive it there really easily, which also made our solution a little bit unique and not something that the Mozambicans sort of really considered. They were looking at trailers and all sorts of other funny things, and we just said, listen, we'll make this happen and put it on the roof. So yeah, this was really a training exercise to show the Mozambicans what can be achieved in a really affordable, simple manner. And we were able to give them depth and temperature measurements in and around one of their harbors. And then we also used that opportunity for laying a whole bunch of sensors in the water. So these sensors will be coming out in February, and that'll give us an idea of what the sea temperatures have been for the past year and a half. So the instruments can generally be under the water for 2 years. Because it's always going to be to find it again. So we've taken GPS marks of where it's going to be. We're going to have to get the same team of divers. This was deep at about 40 meters. So you can't be there for very long to be able to lay those. But yeah, the divers all reckon that we'll find it, so yeah. So this is a survey. I'll play it really quickly, but just in the Port Elizabeth Harbour. So this is the very same vessel working in to do a survey. Generally, they would use a tugboat that they would drive up and down to take the measure. We're doing it completely autonomously with a solar boat. So yeah, the Portnet really, really happy with what we were doing. I know that we're almost out of time here. So this is just to give you an image of what type of the data looks like. Again, this is a measure of our North End Lake. So we're lucky in that we have that lake handy for being able to take, for performing any of our trials. This is what happy interns look like. So this is obviously a very rare photograph, seeing an intern with a smile. But this is a really interesting project in that the interns themselves were able to build our next survey vessels. They built it from manufacturing the plugs, manufacturing the molds, taking the first parts out of those molds, and then doing the electronics in those molds, in the part. So this is another clip of the build. I'm not going to share that, but yeah, this is what the final product sort of looked like before we equipped it with the satellite, with the solar, because we needed to give it a bigger weather window. So this is not being innovative. This is simply using what we know works. And the racing rubber ducks out there are able to cross our oceans really, really quickly. So we stole with our eyes and built something based on what we know works and can go over the rocks very easily. You can deflate it and put it inside a bakkie if you need to. So it turned out to be a really, really successful build. And yeah, this is what they finally look like once completed. And this is the final sort of image of what it looked like when it was operating. So this was the second trial that we did in Mozambique, having a look at those marine heat waves that we discussed earlier. Obviously, being light, we could mount these vessels on a boat to be able to take them out to sea. So working off Bazaruto Island. This is what the island looks like if you look from the beach. Absolutely beautiful, flat. But when you get out to sea, not so much. Yeah, so this was one of those life's lessons where you think it's going to be a beautiful day, not necessarily always. So this is completely autonomous motion. The boat is doing everything itself, doing survey work. And we just happened to be out there when we found it, doing its thing. It also got caught by these fishermen, and is a robot. So it's simply going from A to B. That's all it knows how to do. And when these guys took it or grabbed it, it decided to fight them because they stopped it going from A to B. And they were exhausted when we finally were able to rescue them. But yeah, this is sort of where we're headed at the university at the moment. So I think just to recap, like I said at the beginning, you need to be told everything 3 times. I've shown you a little bit of what ENSA does, what the problem is, and then obviously what we are working towards in solving that problem. And yeah, that's the end of my talk. And if there are any questions, then feel free. This is a photograph. I think this is the best of us. It's not necessarily. I don't think it leaves anybody with any type of comfort after seeing this is who we really are. Thank you very much.
And Andrew, thank you very much for that fascinating presentation. I live in the Western Cape of South Africa, in the Overberg and Overstrand area. And if you are in this area this week, you know exactly how crucial it is to have accurate weather predictions and have accurate climate data, as every bridge in this area has been flooded and wiped out, and the infrastructure in the area is just in tatters at the moment. So it is actually very, very important work that you do. And first of all, thank you for inspiring the young generation coming up. See smiling faces, they're having fun, but at the same time making a difference. And that is fantastic. Also to see how the engineering science is now making a difference and giving us the data that we need to fight climate change. That was a really fascinating talk, but also giving legitimacy to the weather data and the climate data that is out there. We see that spread of data instruments all across the ocean, and you understand how people can come up with those models. So thank you also for showing us the bigger picture, and also the bigger picture of science in South Africa. So we really appreciate your talk. So with that, I would love to open the floor to questions. You can use your reaction tools, you can raise your hand, and we would love to hear from you. I see there's a comment in the chat from Zuzile Hlatswayo. What level of investment and support is this kind of innovation receiving from our government? I ask this because I see the importance of the work your institution does. Thank you.
Yeah, so let me answer that by saying that I think as far as the government goes, we get absolutely fantastic support through an organization called SAIMI, which is the South African Institute or South African International Maritime Institute. And yeah, they are looking at various ways of supporting our work and various others. The other funder that we have at the moment, and I say funder, that a fantastic support infrastructure, is SIAB, which is the South African Institute for Aquatic Biodiversity in Grahamstown. They, like I mentioned earlier, they've made their facilities available to us. And so they have boats and experts in various fields, and they're happy to assist with our student education, and so real fantastic support from them as well. So I think the government has put these institutions in place, and those institutions are now supporting us. So I think the mechanisms are working. I think on a global scale, we cannot compare ourselves to what's happening in the United States or any of the sort of richer countries. I think we're doing what we can, and our solution is to use affordable robotics and get as many instruments in the water as possible, rather than using one really expensive instrument. And yeah, but I think the question is, I think everyone's trying to do their bit, and they're seeing the value in it. So one of the other things I can add, and the number that gets brandished around, is that there's 40 million people that live on the Western Indian Ocean, so that's our east coast. That's 40 million people depend on an income or sustenance or the life of the sea. So we've got to look after it, and just looking after our coastline isn't good enough. We need to know what's happening with our neighbors as well. So Mozambique has a coastline that is longer than South Africa's. So we need to know what's happening in their coast, on their coastline as well, because that water gets to us. So we need to be monitoring more than just our own coastline. And South Africa's government is certainly playing a part in assisting with that as well. So it's become quite a special community, of oceanographers and supporters of what's actually happening up our coast. So when it comes to measuring again, the number that gets brandished around is that if our sea increases by 1 degree, then we'll need to find a new food source. Based on the technology that we have at the moment, using a satellite, it's very difficult to tell 60 or 40 million people that they're going to have to find food somewhere else, based on really difficult to interpret data. So taking actual measurements of what's actually happening is vital.
Thanks, Andrew. Then over to Andrew Mariti. Please ask your question.
Okay, thanks, Johan. Andrew, I must say it's a good thing that your department at Nelson Mandela University is trying to explore this marine robotics. But now, just like the space exploration, now the high pressures and the low temperatures in the ocean, won't that disturb the thorough, follow through on this project? Because now we are aware that climate is changing and it's affecting the whole lot of atmospheric and the oceanic areas.
Yeah, so if I can try and answer that, you're 100% right. The one thing certainly is affecting the other. And I think the old saying is that if you're going to panic, let's panic first. And I think that that needs to be the rule, in that we need the data to find out how badly we need to panic. We need to find the data to come up with a plan of what we can actually do about it. But we know that the sea certainly is increasing in temperature. The storms are getting more violent. The fish stocks are becoming more and more. But Earth has a way of healing itself. I think it could start earlier rather than later. So, but yeah, to answer your question, certainly one thing is connected to the next. It's very difficult to get away from that.
So I guess, Andrew, you are now and again developing and improving your designs of these marine robotics.
Yes.
To withstand what we are looking now for the future in terms of climate change.
Yes. So we are developing new instrumentation all the time. We're developing the robots themselves. We're developing better control strategies for them. So we're doing the engineering work, and we rely on the oceanographers to tell us what they need the data to tell them. So they inform us as to what accuracy they need on a CTD instrument, for example, the conductivity, temperature, and depth. We rely on them to tell us whether or not they need a fluorometer, for example. The ocean is responsible for a lot of photosynthesis, and you need to be measuring all of those parameters. So yeah, it's a very for me, it's I'm learning my way through it as well. In that when the marine robotic problem got posed to us, we said, right, these are the abilities that we can put on the table, and the oceanographers were thrilled that we could add some sort of value, and we're finding that there's more and more that we can do. And I'll give another little example of one of the projects that was undertaken. Is that there was a question asked when a shipping lane was proposed for one of the new harbors, and the question was how that would affect the bird life. And so an egg was developed that was placed underneath a penguin, and the egg had sensors in it to measure the heartbeat of the penguin, and we could then measure the stress levels of the penguin. So as the noise and the traffic of the ships increased, we could measure the effect of the stress on it. So it's such an incredibly wide field. There are so many problems that need to be solved, so many answers out there that we need to find. So marine robotics is absolutely fascinating.
Okay. No, thank you, Andrew, and good luck on your endeavor.
Thank you very much. Thanks to both Andrews. The story about the penguin is truly mind-blowing. A warm welcome to Ben from Rwanda. Interesting presentation, he says. Has the use of ocean gliders ever successfully informed actions to combat climate change?
So the sad truth is very little has done to combat the effect of climate change. We certainly know it's happening, and we're a really greedy species, and to try and change our habits is really difficult, but possible. I think we all need to have hope. And so the ocean gliders are measuring data. The data is being collated, and we are able to show that that climate change certainly is a factor. It's one of those effects that needs to be measured over a very long period of time. And the instrument requirements are they are significantly tight in that they're really high spec pieces of equipment to measure a degree, a 3 decimal point degree change, because we get the information, daily. So yeah, it's one of those things that we know it's happening. We need to measure at what rate it's happening.
Thanks, Andrew. Another question from Zuzile. Apart from monitoring for weather-related phenomena, can the available technology be used in maritime conservation in some way? If so, how?
Yeah, so I think I'll answer that a little bit with the egg situation. Example is that I think in the old days, if you were measuring the amount of fish stocks, then the way to do that would be to measure the amount of guano produced by the penguins, the penguin being the most prolific predator that we have in the ocean. And but we don't necessarily need to measure the fish or the guano anymore. We can measure the weight of the penguin. So there's little scales that have been developed that as the penguins get onto the rocks and the same penguin walks across, we can geotag the penguins so that we can monitor them with the satellites and find out where they're going and how far they have to go to get their fish. So there are fantastic opportunities for using engineering in conservation. I think it's simply a case of what questions need to be answered. Additionally, if you look at on the rhinos, for example, we're using airborne drones. These are unmanned autonomous vehicles that you send into the sky for monitoring rhinos and what their habitats are and what have you. So technology is playing its part, and I think there's heaps of questions out there that we are able to answer as a result.
Thanks, Andrew. Andrew, I just want to check with Maret. Maret, have I missed any questions in the chat at the moment?
No, you haven't, John.
Thanks, Maret. Andrew, if I don't see any further questions from the audience, I would like to thank you. I think there is nobody like an engineer to give you the facts straight up about so many things. And engineers tend to have an understanding of how systems work that's quite unique, and relaying those facts. So we really appreciate your lecture this evening, and as Leadership for Conservation in Africa, we really look forward to continue working with you and telling the story of how you solve problems also in the climate change arena. So it would be good to continue this relationship. Thank you for your time.
Thank you so much for the opportunity. It's a very unusual request, and I'm so glad that that I was asked. Thank you so much.
Thank you very much, and a good evening to everybody. We'll see you again next week.
Thanks.